Alright, hello everyone. It's the Proof SAS here with another optimization problem in calculus. This one is cool in my opinion because it involves some 3D volume geometry. We're going to inscribe a cone inside a sphere with constant radius A, and we want to find out what the maximum volume of this cone can be. So a thing that will help us out, aside from the constant radius A, right here, is that we will define a height x, which will be the height from the base of the cone all the way to the center of the sphere. That's what this C represents over there. And now, what do we need to do to help us? Well, we need to create a volume function. Since the radius is going to be a constant, our function will be purely in terms of the height from the base of the cone. So it will be v of x. And well, what is the volume of a cone? It is simply 1/3 the volume of a cylinder. So in other words, if you form 3 cones together, smash 3 cones together, you can get a cylinder. That is a nice fact from Cavalieri's principle. But anyhow, the volume of a cylinder is simply 1/3 times pi r squared times the height, because you're getting a cross section of a circle and you're basically raising it by a given height. Okay, but h and r, we now need to swap those terms with the variables we are given in this problem. Now r, if I'm not mistaken, is going to be this unknown length here, which is the missing side of a right angled triangle. And what theorem can we use to find a missing side? The Pythagorean theorem. So r squared simply equals, the 2 sides squared add up to be the hypotenuse. R squared plus x squared equals a squared. And to solve for r squared, I just subtract x squared from both sides. So r squared becomes a squared minus x squared. All right, and what's h? Now, here we might differ. Tell me if you think this makes sense, but I think the height has to be, it can vary with the radius and the height at the center as well. So I think h is going to be x plus a. If you think it's x, feel free to write down your reasons for your disagreements. I could be wrong, but this is how I set up the problem. H equals x plus a. And now I'm basically going to substitute these constraints into this volume function here. So v of x is going to become 1/3 times pi. R squared will now, will become a squared minus x squared. H will become x plus a. Okay, cool, we're good. And now all we have to do is expand out this polynomial. So we're going to get 1/3 pi a squared x plus a cubed. Use whatever method you're comfortable with. You could use multiplication using area grids, or you could use FOIL. A cubed, this is minus x cubed. This is minus ax squared. And now we want to take the derivative of this function. So dv by dx, we apply the power rule carefully to both sides in terms of x only, and a is a constant. We should get 1/3 pi times a squared minus 3x squared minus 2ax. And that equals 0. Now, there are multiple ways we can solve that quadratic equation. Factoring, factor theorem, completing the square. But just to beat a dead horse and not expend too much of our thinking energy, I'm just going to use the classic quadratic formula, which I like to write as x equals the axis of symmetry equation plus or minus the square root of the discriminant over 2a. And I like to write it this way because your solutions is basically you're taking what the axis of symmetry, where the center of the parabola is, and then you're looking at some tiny distance to the left and to the right, and those will correspond to the roots of your equation. If you want intuition of this, you can take a look at Potion Low's magnificent midpoint formula method. I really like that, but okay, let's write this down. This becomes 2a over 2 times minus 3 plus or minus, I'm unfortunately going to have to delete some space, delete some writing to make room now. This is then square root of minus 2a squared minus 4 times minus 3 times a squared all over 2 times minus 3. Hope you can see that. And then that becomes 2a plus or minus square root of 16a squared, which is a perfect square, which means, yes, technically you could factor this, but it's not quite easy. I think the way to go is this, divided by 2 times minus 3, which just becomes 2a plus or minus 4a all over 6, which means that x equals, upon simplification, actually no, let's simplify this out. We could get 2a plus 4a, which is 6a divided by 6, which equals 1, or we could get 1, I'm sorry, I meant positive a. And sorry, that should be a minus 6 here. Minus 6 here, minus 6. You could get a negative a, or x equals minus 2a over minus 6, which is 1/3 a. But once again, as typical of optimization problems, we have to pick the correct solution, because we don't know whether this will minimize or maximize, and the way we do this is by using the second derivative test. So if we already know that our derivative function for the volume dv by dx, if we know that that equals 1/3 times a squared minus 3x squared minus 2ax, then if we differentiate that further again, we will get minus 6x. The a squared cancels out because that's a constant. The 2 gets brought down, minus 1 on the exponent, that becomes a minus 6x. Don't forget to divide everything by 3. Minus 6x minus 2a, all divided by 3, which becomes minus 2/3, minus 2x minus 2/3 a. That's dv by d squared dx squared. d squared v dx squared. Sorry, that's a bit scrunched there. And we want to test, we want this to be a maximum, right? So we want to set this to be less than 0. So moving that around, we get, let's see, well, we have two minus terms on the right hand side, so we can divide a -1 on both sides. That will change the sign of the inequality. So we get 2x plus 2/3 a is greater than 0. And then if we subtract that, we get 2x is greater than minus 2/3 a, which if you divide by 2, that just becomes x is greater than minus 1/3 a. Good. And that's consistent with the work that I've shown. So then, the only value of x which will work to maximize our cone's volume will be this guy over here. Since 1/3 a is greater than minus 1/3 a, and minus a is less than minus 1/3 a. So now all we have to do to solve this problem is go and take this and then plug it into our volume function. The maximum volume of a cone under this constraint will therefore be 1/3. Okay, let's see. We recall it's 1/3 pi a squared x plus a cubed minus x cubed minus ax squared. Correct? Oh wait, well, let's go and put it in the factored form. A squared minus x squared times x plus a, right? So then we can simply put in x, which is 1/3 a all squared times 1/3 a plus a, which should become 4/3 a. And then this just equals 1/3 pi times a squared minus 1/9 a squared. This becomes 4/3 a. A squared becomes 9a squared over 9, so that's 9a squared minus 1a squared at the top. That becomes 8a squared over 9. We get a 1/3 pi 8a squared over 9, and then times by a 4/3 a, which simply becomes 1/3 times 8/9 times 4/3 pi a cubed, and that coefficient of fractions, free fractions being multiplied, becomes 32 over 81 pi a cubed. Right. And now, to check that our answer hopefully makes sense, we understand that the original volume of the sphere is 4/3 a cubed, right? Because a is the radius of the sphere. Since both of these are proportional by a cubed, I suggest at this point we go and plug in these values of 32/81 pi and 4/3 pi into the calculator and see what we get. In fact, I think it should make sense because 32/81 pi, that's a proper fraction, which is less than 1, because it doesn't exceed 81 in the denominator here. And that is less than 4/3 pi, which is an improper fraction. That is greater than 1. And let's go and check. 32/81 times pi. That's around, to three significant figures, 1.24. And 4/3 times pi. That's 4.19. So it makes sense. Our sphere should serve as an upper bound of our volume, and the volume of our inscribed cone should not exceed that volume. Okay, I think that makes sense. I think it's possible that you could dispute the x plus a here and argue if it's x if you have to constrain that cone such that its apex or its tip of the point has to lie within the center of the cone. But I don't think we need to make that requirement, hence why I made it x plus a. Please feel to let me know if you came up with a different parameterization or different substitution of variables for that. Otherwise, I think this is the correct answer. But overall, regardless of whether the answer is correct, I hope you understand how the process works because, hey, everyone, even mathematicians, are human. We all make mistakes. So yes, that is the end of that magnificent journey. Please like and subscribe if you enjoyed this video, and let me know any further comments, questions, and concerns you have. Until then, please have a nice day. See you.